Okay, so we're very happy to start this morning's session with Andy Lucas from University of Boulder, Colorado, who's also an organizer of the program and will tell us about viscous electron fluids.
All right, yes. Okay, so yeah, I mean, of course, feel free to ask questions during the talk. I would sort of prefer that versus having everything at the end. Yeah, so indeed, I think most of this will be a sort of review talk. If there's time at the end, I have a few remarks on some, I think, more kind of forward-looking theoretical work that would be nice to connect with experiments. But for most of the talk, I'll be discussing sort of aspects of the theory that I think have been by now pretty well established in experiments. Yeah, so I've been working on this for about a decade now. Today I'll be sort of highlighting work done by my current and former students in the first row. Jack is here and will be speaking later today. And then I'll be focusing on my kind of longstanding collaboration with the PIs at UCSB, Anya Jayek and Andrea Young and their groups. Okay. So let's first sort of take a very big step back and sort of ask why hydrodynamics in the first place. If we're not talking about liquids and gases, then like water, air, etc., then why would we expect hydrodynamics to be relevant at all? So yeah, let's take a step back and think about what's happening in, let's say, the air in this room. We have some very large number of molecules. Even if we treat them classically, the initial value problem is quite involved. I could specify the position and initial velocities of every molecule in the room, and I would have some absurd number of degrees of freedom to solve for. So if I'm looking at F equals ma, then obviously this is a sort of waste of computational resources, not that they would even exist. So therefore, we sort of turn to what in modern lingo we could say is an effective field theory for the description of the molecules in this room. The goal is not to describe, where molecule 10 to the 20 is at time t, but rather to describe experimental observables, things like the temperature, the pressure, the sort of momentum density or fluid velocity, right, in some region of the box as a function of time. And these kind of collective variables don't care about microscopic details like the fact that air, has more nitrogen than oxygen. Okay. So this effective field theory is pretty universal. It cares about symmetries and conservation laws, et cetera, but not the fact that we're talking about molecules in this room as opposed to potentially at least electrons in a solid. Of course, the downside for that universality is that hydrodynamics is not a sort of panacea, right? It's an effective field theory that only makes sense on sort of large length scales. And what do these length scales need to be large compared to? Well, they should be large compared to the mean free path between collisions. Okay. One can maybe define this in a self-consistent way if desired, but for the systems we'll be talking about today, I think, at least in principle, there's a kind of fairly explicit microscopic understanding of what this mean free path should be. Okay. Now, one can sort of bring to this problem all the modern technology that we have for effective field theories, but for the purposes of this talk, it's easier to kind of proceed the way Landau would have about 100 years ago. So the philosophy goes like this. We've already observed that maybe, or at least asserted to you, that on sort of long length scales compared to the mean free path, there may be kind of an emergent collective description of the system in terms of a few degrees of freedom. Let's suppose for the moment that we really had only one conserved quantity, which is like a charge or a mass density. We may also consider that, I have a conserved charge and there's some kind of statistical homogeneity in space and time. Maybe I have time reversal symmetry, rotational symmetry, and so on. So now I'm going to take these first two bullet points and sort of build my hydrodynamic equations based on symmetries and kind of the philosophy of effective theories. So first, my equation of motion will be just the conservation law for charge. Physics is local, right? So a charge can't teleport from one region in space somewhere else. It has to move locally. And then I need to specify a constitutive relation J for this current as a function of the conserved density. Otherwise, this equation is underdetermined. And now I say, well, J has a vector index, rho is a scalar. So I should act with sort of spatial gradient operations, right, to convert between the two. And that's perfect because remember my small parameter governing the effective theory was the mean free path divided by the scale over which the system is varying, or equivalently little l times the gradient operator. So we can precisely see that this kind of derivative expansion is sort of equivalent to this kind of EFT expansion that we described before. Okay. And usually in hydrodynamics, one would just keep the sort of leading order terms. Usually the first derivative corrections are enough, but in principle, you should keep in mind that this expansion has higher order corrections, and in particular in an electronic context where you may not be deep in the hydrodynamic regime, you might be looking at physics comparable to the scale little l. It's worth keeping in mind that there are these corrections. Right. Then the loop is sort of closed by asserting that we should flow towards equilibrium, not away from it, and that means this combination A times little l should be positive. Okay. And again, one can sort of make this all a little bit more sophisticated using EFT methods, but in a nutshell, the arguments are the ones given here. Okay. So for ordinary liquids and gases, one just carries out this same procedure, but keeping a few more degrees of freedom around. In this talk, we'll focus on essentially just mass or charge and momentum conservation given here. And with Galilean invariance, mass and momentum conservation, one arrives at these equations. Okay. Unlike in the previous case, in this setting, there are some terms that in the constitutive relations that come with no derivatives. That's sort of allowed now that we have basically two conserved quantities, one that's even and one that's odd under time reversal. And that's sort of responsible for the richness of the Navier-Stokes equations that's not present in the theory of diffusion for an ordinary charge. Okay. Viscosity is sort of playing exactly the same role as the diffusion constant from before. It's, yes.
Sorry, I'm not very familiar with this formalism. So it seems within this formalism, you cannot get the relativistic system. You cannot describe that.
You can, it's just a different set of symmetries. So here we're using basically non-relativistic boost invariance. And this gives you the sort of textbook Navier-Stokes equations.
You change an input symmetry and you get another formalism. And
yes. Yeah, if you input Lorentz invariance instead, then the constitutive equations are different and they match the relativistic.
And previously you get the diffusive motion, like can you go beyond the diffusive motion? Like ballistic and crossover, whatever.
So, okay, I'll talk a bit more about ballistic transport later, but to sort of answer the question now, you should think of the ballistic regime as kind of a specific resummation of this whole series.
Okay, thank you.
It's very non-trivial to see purely from the hydrodynamic perspective, but if one has a microscopic kinetic theory for the system, then in principle it's sort of straightforward, and there's a well-established way to then see hydrodynamics as one limit of the kinetic equation.
Okay, thank you.
Yeah. Okay. All right, so far I've argued that hydrodynamics arises as an EFT, and in particular is sort of independent of microscopic details. So you might ask, then I think for the audience at this workshop, there's some interest in strongly correlated electron systems. Why don't we sort of look for hydrodynamic signatures in observables that are natural for this community? So the most natural observable here would be the electrical conductivity, or 1/resistivity of a metal. Ohm's law, at least with rotational symmetry, right, says that the current J should be proportional to electric field E times this constant sigma. So why not just look for the imprint of viscosity, for example, in this coefficient sigma? And we can give a simple argument that this is not going to work. So let's assume that the system is spatially homogeneous, at least statistically. This is F equals ma, Newton's law. So on the left-hand side, I have the rate of change of momentum of the electrons in the system. On the right-hand side, I have the force, acting on this charged fluid from an external electric field. And okay, we usually, would measure and experiment the Fourier transformed version of sigma. So let's do that. We find that sigma of omega from this formula will at leading order have this kind of pole. So I over omega times what's called the Drude weight, which for Galilean fluids would be the charge of the electron, E squared over m times its mass, weighted by the number density. Okay. So in particular, the omega to zero limit is kind of sick, and sigma is infinite. All right. This conclusion does not depend on Galilean invariance. I think at least 10 years ago, this was a sort of common misunderstanding. I hope that it's by now changed, but this conclusion only relies on momentum conservation. Okay. So if you ever have momentum conservation, the conductivity is not well defined, at least in the DC limit. Okay. That's maybe surprising because if you go to an undergrad lab and you measure the resistance of a metal, it's not zero. So evidently momentum is not conserved in metals. And I would say morally the cartoon that I usually give for what's happening in a typical metal is then the following. So I have metals are kind of dirty. We don't like to talk about this often because it might feel insulting to the experimentalists who are working very hard. But most metals are kind of crummy microscopically. There's a lot of dirt, impurities. So electrons are kind of moving in this inhomogeneous landscape. And from Nether's theorem, we know, of course, that this inhomogeneous landscape means that momentum is not conserved. And the situation can be even worse. We may have a very clean crystal, but a crystal only has discrete translational symmetry. So discrete translational symmetry is not enough to have momentum conservation. You only have crystal momentum conservation. There are Umklapp scattering processes in metals between electrons or phonons that can also relax the momentum that's defined in the Navier-Stokes equations. So basically, the combination of these two factors means that in typical systems, there may be no reason to expect that the momentum conserving scattering rate is sort of large compared to a momentum relaxing one. And in this case, we would expect that if there's a hydrodynamic description at all, it's going to look like the ordinary diffusive one that I mentioned at the beginning. Okay. There are two ways that we might try to sort of cure this picture. The one that had certainly inspired me, and I think many others in this community a decade ago, is this middle picture. You might imagine that in some kind of strongly correlated metal, it may still be a bit dirty. I mean, if you ever see a chemical formula with an X in the numerator, this means that it's not a particularly clean lattice microscopically. But nevertheless, if the system is very strongly correlated, you might imagine that interactions between this sort of soup of excitations is so strong that even though it's moving through a somewhat inhomogeneous lattice, it still might be reasonable to think about a kind of emergent fluid of this very strongly interacting soup of potentially non-quasi-particle, non-Fermi liquid excitations moving around in this kind of inhomogeneous landscape. And it might be possible here, as I've tried to schematically depict, that this purple scattering length is still short compared to a momentum relaxing scattering length. Okay. It might not be so straightforward to define those scattering lengths, but morally you might imagine this is one possibility. But today I'll basically be focusing on another possibility, which turns out to be easier to realize and to quantitatively connect with experiments. If it's a little bit less inspired, you could just sort of ask a material synthesis friend to do better and to make a very high quality material with few impurities. And in that case, even if the momentum conserving scattering length isn't really that much shorter than it is in a typical metal, as long as the impurity scattering length is enormous, you could still have a kind of hierarchy of length scales where the electron-electron or momentum-conserving collisions occur much faster than the momentum-relaxing collisions. And in this regime, you might hope to see viscous electron hydrodynamics arise on some range of length scales. And I would say by now there are hundreds of experiments that have at least seen kind of the signatures or the onset of this viscous regime in many materials. Most of them are based on graphene, but there is sort of a smattering of other experiments on lots of different compounds that also have at least some evidence for hydrodynamic behavior.
Andy, so here you're mostly referring to impurities.
Yes.
At some point you mentioned umklapp.
Yes.
How do I make sure that umklapp is not going to shorten the momentum relaxation scale?
Yeah, so the sort of canonical argument here is that you want the Fermi radius, the radius of the Fermi surface, to be sort of 1/4 or less of the Brillouin zone. And then in a sort of two-body collision, you don't have enough kind of crystal momentum to wrap the Brillouin zone. So the reason why most of the experiments that one does in this field are on these 2DEG devices like graphene or gallium arsenide is precisely because they have tunable and extremely tiny Fermi surfaces. So in some sense, there's like a good reason to expect that this is even possible. There are experiments on 3D materials that actually don't have small Fermi surfaces, but people still find at least some evidence for hydrodynamic behavior in transport. And there are some kind of ab initio efforts that have been made to understand why. Maybe one just calculates scattering rates, and it turns out that the umklapp ones are suppressed by a factor of 20, for some funny reason. But yeah, that sort of, does that answer your question?
Yeah. How about other materials like cuprates or heavy fermions?
I mean, I don't think, I'm not sure if there's, I don't actually know of one experiment off the top of my head that claims to really see a hydrodynamic signature in this.
Oh, I agree.
setting.
But at least some people claim that some cuprates can be relatively clean.
But I think when they say clean, they may mean something different than what I mean by clean.
Sorry, there is one from the group of Philip Moll. He showed in praseodymium cobalt this material in heavy fermions. They show that there is hydrodynamic.
So, okay, I actually removed some slides on palladium cobaltate because the talk was getting too long. I guess sort of the short story there is I think originally we did think that there was hydrodynamics in palladium cobaltate, but I think there's been follow-up work that seems to imply that it's not, that it's a ballistic system. Yeah, there are, and one of the mysteries in palladium cobaltate is that it has a very large Fermi surface, so it's not clear why Umklapp would have been suppressed. Yeah, again, I would mention, at least kind of looking from this perspective, one possibility for a material like palladium cobaltate is that it just so happens that the collisions that are non-Umklapp are much faster than the ones that are Umklapp. For example, maybe you have a kind of flattish region of the Fermi surface, so collisions are very fast along that branch. This is one possibility. Yeah.
Just as he said, in cuprates, there is as well this Planckian dissipation that people, they claim it's the highest ratio between viscosity and dissipation around these critical points. And this is not the hydrodynamic. So Jan Zanen showed that it's in the regime of hydrodynamic, no?
So, okay, so I would say if you have a very strongly correlated fluid, there are indeed, these bounds kind of coming often from ADS CFT that viscosity over entropy density is extremely small, and we think, maybe at least morally kind of as small as possible. But it's sort of tricky, right? Because if you're in this situation, how do you even define the viscosity? If the impurities are somehow central to the story, one wants to define viscosity by sort of interpolating to a limit which has honest translation variance. So you can, do the honest hydrodynamic expansion in the way I described, and one of the coefficients is called viscosity. That's maybe sort of a technical subtlety. Maybe the more practical response would be that, as I mentioned, I don't think there's an experiment that has really seen convincing evidence for a signature of viscous transport in a cuprate. And I will show you a number of them in graphene. So this is something that's very testable experimentally. And it would be amazing if someone could do it in a new family of materials, but to date, I don't think it's been done. Yes.
To Dan, are we done with this? Or a different?
Go for it.
If I just have electrons in a vacuum with no disorder, no atoms, can it relax momentum or not?
So if you have only electrons, in principle, I would say the answer is no, although only electrons is a little dangerous because Coulomb interactions are long range.
Yeah.
Right, and so long range that it
Gellium.
oil. Yes, exactly. So
Gellium and.
Yeah. So in this context, I would say maybe.
Isn't really asking, do the electrons steal momentum from one another, resulting in momentum relaxation?
No. The collective momentum is still conserved.
Of the whole.
Of the whole system. Yeah. And in Gellium, what happens is basically the sound wave that we're familiar with in ordinary fluids just becomes the plasmon.
Yeah.
And the fact that you have the 1/r Coulomb interaction means that this mode looks gapped. Right. It has a constant.
Yeah. Well, there's transverse modes that aren't. But, okay. Anyway, good. So the center of mass momentum is conserved, and it's not unless you have some external thing like disorder.
That's right.
Lattice, and that's the key point.
That's right.
Great.
Okay. Yeah. There's a nice review article of mine that it's a bit old, so it doesn't have so many of the experiments, but it's, I think, still kind of morally a good place if you're interested in kind of learning this subject. Okay. Yeah, let me say a little bit about materials. So I mentioned that you have to ask your materials friends to do better. So I think certainly in the 2D materials setting, the kind of main revolution that made this whole field possible was new techniques to make very clean 2D systems. So in the graphene-based context, to make the story short, this basically amounted to more stable ways to grow your sort of stack of 2D material, one layer of which is let's say monolayer graphene in this example. In a nutshell, the old way people used to grow these materials led to a lot of chemical bonding between the atomic graphene layer and the substrate. You can't suspend like a single membrane of carbon in a stable way, just mechanically, right? So usually you want to sort of put it on something to make it more stable, but that's something, if it's silicon dioxide just bonds with graphene, and it's kind of lousy. But then people realized to use another sort of material with a very similar band structure that's an insulator, HBN, and in 2D systems like graphene, the dominant kind of disorder usually arises from ions out of the plane, whose sort of Coulomb potential causes what are called charge puddles. And when you image the charge puddles, in the old versus newer samples of graphene, you can see there's like orders of magnitude improvement, both on the length scales over which the system looks homogeneous and on the kind of amplitude of the charge puddles. Okay. So this is kind of on the material side, in a nutshell, what made hydrodynamics possible to observe. Now let me talk a little bit about what you might do in an experiment. I don't think it's as obvious as in an engineering setting. If you asked like, well, how would I see Navier-Stokes equations in the fluid in this room? That might seem like a sort of silly question because there's so many things you could think of doing. But in the electronic setting, if you think about the length scales, for example, in graphene, it's usually micron. Time scales are kind of gigahertz, maybe even terahertz, depending on the kind of fluid dynamics you're looking for. So it's not as easy as like, drop some dye and watch where it moves, and then you get a sense for like the velocity field. So, okay, what does one do? So thankfully, despite the whole spiel that I just gave you, one can still think of very, at least conceptually, simple experiments that are possible. This was already done by a Soviet physicist named Gurdjieff in 1969. I think his ideas were probably mostly forgotten until after he died. And then, the field became popular 7 years ago, which is too bad. But anyway, he was already thinking back in the 1960s about what might happen if you had very clean electronic systems where you have this sort of separation of momentum conserving versus relaxing length scales. What could you see? And he basically copied, probably Landau's fluid mechanics book because Soviet Union, but he copies some stuff out of that book and translates it to the electronic context and says, okay, in fluid mechanics, if I have just a flow between two parallel plates, I can, let's say in the ordinary fluid mechanics context, I could have a pressure gradient between this side, and I could ask, what's the flow rate of the fluid right through the channel? And this is kind of analogous to Ohm's law, right? Except I would want to replace pressure gradient with voltage and, mass flow with current. But one can translate from basically what's called Poisson flow in fluid mechanics to what we now call Gurdjieff flow in a solid state system, and predict the resistance per unit length of this device, which is sort of the most natural way to report things. I'll do this in a moment, at least tell you the scalings, but you should think on the next slide that the resistance per unit length of this device is going to be basically 1 over the width of the device times a kind of effective momentum relaxation rate. In an ohmic system, this thing is constant. It's like the time to hit the next impurity. And this 1 over width in a 2D system is the analog of like the resistance of a device is inversely proportional to the cross-sectional area. So, okay. So now let's think about the various transport regimes that we might be in. So first, if the device is really big, then we should just see kind of scattering off of impurities in the bulk of the device. This is what I would call the ohmic or diffusive regime. And here the time scale right here is basically just set by the inverse of the momentum relaxing mean free path. So this is a kind of conventional regime where the resistance of this device is inversely proportional to width, which is the 2D analog, right, of our textbook formula relating resistance and resistivity. Okay. In the viscous regime, which unfortunately turns out to only occur when the width of the device is smaller than this geometric mean. So it's not enough to just have the channel sort of short compared to the momentum relaxing mean free path. You need, unfortunately, this geometric mean, but okay. If you happen to lie in this window, then the hydrodynamic equations predict this scaling LEE times 1 over width cubed. The 1 over width cubed here is coming essentially from the fact that there are 2 derivatives in the Navier-Stokes equation when you have viscosity, and so those 2 extra derivatives give you 2 extra powers of 1 over width. There was a question earlier about ballistic transport. This is what happens when the width of the device is so tiny that even the electron-electron collisions are negligible. In this regime, the particle basically just bounces from one wall to the other. And the resistance, basically this rate is just 1 over W, the time to bounce between the walls. There's subtleties in this story that I'll sweep under the rug, but morally this is the answer. And so in principle, this looks pretty promising. We have sort of 3 different scalings with width. So if we just, make a bunch of samples with different width, we can try to ask, which of these regimes we're in. There's another thing one can do, which maybe is a little more preferable to the experimentalist, which is to instead say, well, in a metal, I would expect that in a conventional Fermi liquid, LEE scales as 1 over temperature squared. So I can instead imagine just changing the temperature of the device and trying to sort of work my way through these different regimes this way. And what would I see if I did that? Well, let's plot this resistance per unit length versus temperature squared, or 1 over LEE. And we see something very counterintuitive, which is that the highest resistance is in the ballistic regime. And then as you heat the sample up and enter this viscous regime, the resistance will actually drop. Okay. And then eventually the resistance is smallest in the ohmic regime, which kind of sets the baseline. You cannot have lower resistance than this.
Just assume the momentum relaxation length is temperature independent.
Yes.
Yeah.
Okay. So in a real system, eventually this curve goes back up because the momentum relaxation rate will increase at high enough temperatures. But morally, one hopes to be in a regime where, if, for example, the dominant source of momentum relaxation is coming from some electron phonon scattering, like there's phonon umklapp and the electrons have to dump momentum into phonons, then you might hope that the temperature dependence in momentum relaxation rate is like T to the 5th in 3D or T to the 4th in 2D, which is potentially pretty favorable to see something like this at lower temperatures. But in practice, it's not always that clean, but morally, that was sort of Gurdjieff's hope. Okay. All right. And the key thing about the Gurdjieff effect that I'd like to highlight is that it's really telling you, if you can measure this plot and you can extract LEE, right, from this viscous scaling, then you're really learning about physics that's invisible in bulk transport, right? You cannot just measure the sort of, wave number independent bulk conductivity and have access to this momentum conserving scattering length, at least in any obvious way. But using this kind of geometry to help you, right, you have access to really a new piece of data about dynamics in the underlying system. So I think that's sort of why you should care about electron hydrodynamics, even if you're not just interested in the subject for its own sake. So if all that you care about is, understanding the physics of, what are the interactions like in this particular material, if there's a hydrodynamic regime, this can be a very powerful way to have some insight into that information. Okay. But, to see it, you do have to be careful and design, sorry, there's a typo, there shouldn't be LEE on the left-hand side. But as we just discussed, to see this hydrodynamic regime, the easiest thing to do is going to be to design some sort of geometry that's has some structure on a length scale that's small compared to this so-called Gurji length, the square root of LMR times LEE. And then, sort of understanding the discrepancy between observed transport patterns versus the ones predicted from, Ohm's law. This can be a very powerful way to access these previously invisible scattering rates. As I'll discuss, actually, I think the cleanest experiments don't just directly look for this Gurji effect. One reason for this is that boundary conditions are a bit delicate. We didn't, talk about that, but in a real experiment, if we don't have perfect control over what the boundary conditions are, then some of these predictions can be a little bit messy. For example, if you have mostly specular collisions with the walls, then it turns out this picture sort of goes wrong. And viscous transport is also sort of only limited by ohmic. So the curve kind of loses all of its interesting shape depending on boundary conditions. So there are other geometries that seem to do a better job, and so this is what we will focus on. I will mention briefly in passing that in principle, the flow of a hydrodynamic fluid through this disordered charge puddle landscape would have imprintable signatures on bulk resistivity, but it's never been seen. This is a very difficult experiment, I think, in practice. So there are some theoretical proposals for what you should see, but in practice, one looks for hydrodynamics in more engineered ways, as I'll describe. Okay. So here's the first experiment that I think did a really nice job of just unambiguously demonstrating the effects of interactions in transport with at least a sign of the effect that matches our expectations from hydrodynamics. So this was done in the group of Andre Geim in 2017. And they basically replaced the channel in Gurji's thought experiment with this constriction. Okay, it's kind of morally similar, but I think of it easier in practice for this reason of boundary conditions that I mentioned. And if you look at the resistance of this device, depending on the constriction width, as a function of temperature, you see that we have this sort of non-monotonic temperature dependence where the resistance first goes down and then goes back up. The back up here is from the temperature dependence and momentum relaxation rate. But in this sort of lower temperature regime, you can think of fitting to this kind of crude formula. So the resistance of this device should scale roughly as 1 over width. That's the ballistic prediction. And then there's an offset in the denominator, meaning the resistance gets smaller as you heat the system up. And this is a hydrodynamic effect. In the data, this sort of solid line that's shown right here is essentially, a quantitative prediction with the right prefactor here, at LEE is infinity. And yeah.
It should not be limited to some range of temperature, like really at low temperature. The hydrodynamic.
So in practice, the hydrodynamic regime often is limited to some temperature range because if you heat the system up enough, then the temperature dependence in LMR makes it very small. And then, this kind of hierarchy of length scales that I described is not reachable. So in practice, in these graphene-based devices, usually this means you're at about 100 Kelvin or below, where the momentum relaxing length scale can be 10 times the momentum serving one.
So it's not better just to focus in really low temperature rather than, because at 100 Kelvin, you have all the phonons, so mainly are scattering by the phonon.
So in graphene, I think the electron phonon scattering is pretty weak. So 100 Kelvin is still okay. Most of the scattering is going to be electron-electron. But indeed, there's a sort of sweet spot where, at too low of temperatures, then maybe you just have ballistic transport. So you need to heat the system up enough so that LEE is, small compared to your device size, but not heat up too much because then the phonons kick in. So yeah, as you can sort of see in this data, right, there is a kind of sweet spot around 100 Kelvin where.
So that's crossing over from ballistic to hydrodynamic transport. That's the claim when you go through this minimum?
Yeah, morally, I would say, quantitatively, I think, the story can be a little bit subtle. And I think there are talks later this morning about complications for this 2D liquid, but morally, that would be the story. I would say, I think what's at least clear is that there's a sort of interaction-driven physics, right, which is pushing this resistance below the ballistic value. That I think is unambiguous. And then, whether one can model this with Navier-Stokes equations or not, that's too strong of a claim, I think. The effect size is like on the order of 10 to 20%. So you're not deep in the viscous regime. But I think it's also true that there's no competing explanation, at least that I know of, for why this resistance would have gone down as a function of temperature, if not for this.
You're about to say what the horizontal lines are. Those are the ballistic transport.
I think I mentioned before, but I can say again. So this solid line is basically a quantitative prediction for what's called Chardon resistance, which is the ballistic resistance.
So the fact that it dips below that means there's some other electrons are scattering off each other.
That's right. So the fact that you get a resistance smaller than that means that interactions are sort of helping the fluid, move more efficiently through this constriction.
Water.
Yeah. Okay. This is sort of one strategy. In the past 5 years or 6 years or so, there's been maybe even more elegant experiments in some respects that one can do. And these are enabled by essentially the discovery or the implementation rather of space-resolved imaging techniques. So you can now imagine not only measuring just this global resistance, but actually imaging how the current is moving locally through the device. So, okay, maybe I'll sort of skip some technical comments, but there are basically sort of scanning probes either based on what are called NV centers in diamond or some nano squid, ... There are multiple ways that one can image current. There are separate probes one can use to measure the local chemical potential, which is a proxy for the number density in the fluid. Okay. If we go to this constriction experiment, in principle, one can, and we did back in 2020, do imaging experiments on this geometry. I'll show you a sort of follow-up experiment because the data is a bit cleaner, but here's the theoretical prediction, at least for the constriction. And you can see that if you can image the flow pattern through the constriction, depending on the resolution that your sensor has, you could clearly distinguish between a sort of ohmic flow where you have this kind of double-peaked structure. The current is concentrated near the edges of the constriction. This comes from what I would call the lightning rod effect, which is sort of an undergrad E&M effect. If you have a corner that sort of sweeps out less than 180 degrees, the solution to the Laplace equation near the corner has diverging field lines. And that effect is responsible for, in ohmic transport, the current bunching near the walls. In the ballistic regime, up to sort of finite size effects in this device, you would see a kind of flat current profile approximately through the center of the device. And in the viscous regime, you instead see this current kind of bunch towards the center of the device. So, 1 is obvious and easy to distinguish from 2 and 3. You just do that by eye. 2 and 3 are a little more delicate in experiment, and one often is relying on some quantitative calculations, comparisons between data and simulation, but at least morally, right, there's some difference here as well. As I mentioned, one can sort of improve the situation.
I have a question, actually. So when doing simulation, I guess you need to impose some boundary conditions.
Yes.
So what are the boundary conditions?
So it's a good question. So, okay, maybe the short answer is that the way boundary conditions were imposed in this simulation is not so good. I think it's okay for this geometry, but yeah. maybe I would say like in this follow-up work done by my student Jack, one can really have much better control over the boundary conditions in kinetic theory and tune them to be.
So maybe to say more, I think for that one, there was some like Fourier domain inversion. So the boundary conditions just imposed by making sure that there was no current outside of that
Out of,
channel.
let's say, not to the surface normal or something like this.
No,
there
zero
shouldn't
as
be any current,
as
of
a
course.
vector,
And
yeah.
what
and
about
then,
the transverse? Like,
yeah,
there's
that's what I
something
think was
to-
not
So
quantitatively like hard to
yeah,
control.
so okay,
Doing the other
basically the way these simulations worked is that you calculated the wave number dependent conductivity, and then you sort of look for one current flow pattern which is consistent with no current flowing through the walls. And the issue is that, but the issue is this is not unique because you can generate like current flows within the walls, but because the conductivity is non-local, that pollutes the signal in the sort of computational domain. So anyway, this is something that we've since improved, and one can impose, I think, somewhat reasonable looking boundary conditions, like you have some fraction of specular collisions and some fraction of kind of diffuse random scattering at the boundary. So yeah, these are the sort of next generation version of these simulations with these better boundary conditions, also a better experimental device. And yeah, so in this geometry, again, you can sort of see something similar. Here, it's a little bit easier to distinguish the ballistic and viscous regimes because they're sort of both flow patterns in this channel and also flow patterns in the kind of dumbbells off to the side. Somewhat ironically, perhaps, it turns out that the strongest like whirlpool-like feature actually is in ballistic regimes, not in viscous regimes. Okay. But one can kind of quantitatively compare the magnitude of the whirlpool here versus here and the current bunching across the cut in this channel. And using this, we were able to recently sort of map out a kind of phase diagram for biased bilayer graphene. So this is basically bilayer graphene in a normal electric field. By tuning the strength of this electric field, you can sort of manipulate the band structure and make it sort of flatter. In 2D materials, one can also tune the density of the carrier density, so basically changing the Fermi energy. And we were able to kind of map out a sort of transport phase diagram with diffusive transport near the charge neutrality point. I don't have time to explain why we expected that. And yeah, ballistic transport at sort of high densities, and then at fairly low densities, but non-zero displacement fields, we see even at sort of around 10 Kelvin, very strong signatures of viscous flow. This is sort of intriguing because this viscous flow turns out to be kind of directly correlated with some other exotic phenomena that recently been found in this same material system. So I think that this is maybe an illustration of using viscous hydrodynamics along the lines that I advertised earlier in the talk, i.e. using kind of viscous transport perhaps as a fingerprint of other interesting physics, not just, looking for the Navier-Stokes equations because it's entertaining. Yeah.
Do you think that this regime is resulting from the flatness of the band?
Yes.
So even in imagine other systems like cuprates, there is some saddle points, and do you think that we can in its part of the Fermi surface we can find this regime?
Potentially, yeah. I mean, I think theoretically there's no objection I would have as long as one can rule out like maybe if the flattish part of the Fermi surface is a pretty small pocket, then maybe it's possible. Yeah.
Maybe one more detail there would be the in the collision dominated regime, you might worry the collision integral can have some detailed structure. So you might hear from that later this morning.
For getting into cuprates, I think the big issue is the electron-electron mean free path is incredibly short compared to everything else. If it's the strange metal regime. So the momentum relaxation length is short, but longer than the electron-electron mean free path. So that means there is a hydrodynamic regime, but it's so tiny. I mean, you could never make it in a device like this. You'd have to have a constriction that's a few angstroms or a nanometer wide, which doesn't mean it's not there, and it doesn't mean Jan Zonen was wrong, but you have to rethink how you measure that.
Maybe in Cooper's, but in strontium reuterates, for instance, so it's very clean, strontium reuterates. So if you take the T2,
It's true, yeah.
So it could be.
But that's a good Fermi liquid at low temperature.
No, it's actually with the magnetic field, it's strange metal, it's really linear resistivity.
Yeah, I mean, maybe, that would
topic.
be great.
Yeah.
Yeah, okay. Yeah, okay. Let me just make sort of a couple of now maybe sort of side remarks because I'm almost out of time, but I'll just tell you a little bit about some things that I think are kind of neat and have been underexplored in experiments, in my opinion, but may be accessible. So the first story will be about anisotropic electron hydrodynamics. So far, we've been working as if the Fermi surface was isotropic, and that's a good approximation for very special systems like gallium arsenide or, bilayer graphene and zero displacement field, et cetera. But, then one can ask a kind of childish question like, well, are these shapes different? Obviously, the answer is yes. If these are the Fermi surfaces of two different Fermi liquids, can we tell them apart in transport? And in our context, basically, would the symmetries of these two Fermi surfaces being different change the hydrodynamics of these electron liquids? This was work done by my first PhD student, Caleb Cook. And we showed that the answer is yes. There are actually some subtle changes to electron hydrodynamics that arise from the anisotropy of the Fermi surface. And okay, maybe I'll just sort of show you quickly what they are. So the first one is this in orange here, what is called incoherent conductivity or incoherent diffusion. In the Galilean invariant fluid, we said that the current is basically proportional to fluid velocity or proportional to momentum density. This is a consequence of Galilean symmetry. But a hexagonal Fermi surface cannot have Galilean symmetry because rotation is part of the Galilean algebra. So, okay, we don't have Galilean invariance, and we actually have, it turns out, a very strong incoherent contribution to the conductivity. The microscopic mechanism here is, I hope, kind of easy to intuit. So if we wanted to say that the momentum density and the current are locked together, even in a kind of quasi-particle kinetic description, that would mean that for every point on the Fermi surface, right, the momentum vector and the current vector, the velocity vector, are parallel to each other. That's a minimum requirement. It's not sufficient, but it's certainly a necessary condition. But now let's take a Fermi surface, in this case a square. We see that the momentum is changing as I move along this kind of flattish Fermi surface, but the velocity is not. It's just a moral cartoon that there's no reason to expect the current and momentum to be locked together. And indeed, the hydrodynamic consequence of that is the so-called incoherent conductivity. This effect could in principle be very large, even in regular Fermi liquids, although it's unfortunately quite hard to observe experimentally. Yes?
What do you mean incoherent conductivity? So for you,
yes, okay, good. So, okay, this is some jargon introduced by Sean Hartnell. So I'm not going to justify the word incoherent because I don't know what was in his mind, but what it means is the following. So there's the electrical conductivity that you measure, and as we've discussed, it's sort of sensitive to things like impurities and so on. But you could imagine that maybe even in a very, very clean sample, at the very beginning, right, we talked about this Drudov formula sigma of omega and you had an I over omega pole, and then there was a plus dot dot dot. So part of what would enter in the plus dot 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 is this piece, and in particular, if D is non-zero here, it would give you a positive constant correction to that Drude weight. So that's the incoherent conductivity. And so in principle, if you had a very clean system with a very sharp Drude peak, you may be able to see, oh, the Drude peak is not, tending down to zero, but there's some constant offset. And if you saw that, that would be this coefficient. In practice, that's not so easy of an experiment, but in principle, this effect is here. And in isotropic single band Fermi surfaces, this incoherent conductivity, this should be 2, not 4. Anyway, but it's a very suppressed effect. So this effect is very enhanced by anisotropy. Even more striking is the existence of a new kind of viscosity.
Wait, Andy, you just said that you didn't have that if you had an isotropic liquid.
So
you're using for an isotropic
for isotropic Fermi liquids, this should be T over Tf squared. So basically, because you have a kind of approximate Galilean invariance,
right,
this effect is weaker. That's all I'm saying. So an effect is sort of very strongly enhanced by anisotropy. This is one consequence of hydrodynamics, or anisotropy on hydrodynamics. Right. The other exciting thing is a new kind of viscosity. So if you open Landau's book, it will tell you, when I used to give this talk, I have some trauma because I always got this attack from people in the audience. But Landau's book indeed says that the stress tensor is symmetric, and the reason for that is because Landau's book is assuming that the fluid has rotational symmetry. But if we have an anisotropic Fermi surface, right, clearly if we start trying to imbue some rotation into the system, we kick the electrons so the Fermi surface rotates a little bit, this costs some energy. The system will try to relax back to its preferred orientation where the Fermi surface aligns with the crystal lattice. And it turns out this gives you a new kind of viscosity that contributes to the antisymmetric part of the stress tensor. In principle, this is experimentally measurable, but again, it turns out to be very non-trivial. The only proposal that I know of, at least, is this work by Caleb, where we argue that local heating rates would be sensitive to the existence of this viscosity or not. And we have some very clever geometries and sort of current in versus out configurations that can isolate the rotational viscosity at certain points. So in this picture, in a nutshell, if you look at this kind of leftmost column, the heating at the center of the device is non-zero, basically only when you have rotational viscosity. So if you can, yes.
By this anisotropic Fermi surface, do you consider either concave or
convex?
Convex.
So that difference would show up in the quantitative prefactors, like when you calculate this coefficient from kinetic theory, it matters.
Because, okay.
Whether the coefficients are non-zero or not is a consequence of symmetry.
But so from the concave to change to convex, so you will have the inflection point. So with that related to the existence of inflection point?
But I think the existence of this inflection point will likely just cause some potential singularities. I don't actually know if it's been worked out carefully in these viscosities. So it may be that the viscosity sort of is much larger, presumably, as you pass through this inflection point. That would be my guess.
I have studied the collective mode of this type of Fermi surface, and the inflection point associated with extra collective mode. So I'm thinking if this is related to that effect. Zero sound mode. Besides zero sound mode, the inflection point associated with extra collective.
And maybe I would say that may have some, it could certainly have some imprint in hydrodynamics. It's probably it's a different calculation, but probably the same physics shows up in this as well. Would be interesting. Yeah. Okay.
Andy?
Yes.
I think it's time to close.
Okay. Yes. So, all right, maybe then the last point I'll mention is that the anisotropy also kind of can strongly affect this ballistic to viscous crossover. We believe that misunderstanding this effect is responsible for this experiment in palladium cobaltate. I'm not sure that the experimentalists would agree with that, but that's at least my belief. So, okay, yes, I can stop here.
Maybe I have time for one question, and we can keep the rest for the break.
How do you know that this hydrodynamic regime in bilayer graphene could be related to these spin valley phenomena?
So, okay,
Is it the same
yeah.
part of the phase diagram or
So I would say, I think the phase diagram is a bit similar. There's also one other curious thing, which is somewhat speculative, but in this part of the phase diagram, Andrea's group has observed in multiple samples that the resistance has some non-monotonic temperature dependence. And I think originally they had thought this is some kind of Kondo-like physics, but a competing explanation would be that they're actually observing this effect, which is very hard to kind of unambiguously see, but it's sort of, yeah. So that it's kind of an intriguing possibility. Yeah.
Okay, let's thank Andy again. So we reconvene in 30 minutes. Break is upstairs. There are 2 coffee machines, one in the kitchen and one on the floor farther down. So don't hesitate to use